Good morning, Miss Neville's Nuggets. We're going to be doing our third lesson about electrical energy. We don't want to forget about that law of conservation of energy, because now we're going to start talking about how we can see or how the law of conservation is illustrated through electricity. Yes, we're going to be taking a deep dive into electrical circuits. As always, feel free to pause this video as you take your notes. If I scroll through the slides too fast, the perfect thing about watching recorded lessons is that you can pause it to get what you need when you need it. Let's get started. So where can we see electrical energy? Well, the easy answer is we can't easily see it. We see this awesome GIF here of electrical energy soaring from one transformer into another. It's important for us to know that in our houses, even right now, we benefit from electrical energy. Any household item that's plugged into an electrical outlet is powered by electrical energy. So let's look at the basics of an electric circuit. When we look at this circuit, its power source, okay, its power source is a battery. We're going to talk about how not all electric circuits have the same type of power source later on. But for these purposes right now, this electric circuit is powered by a battery. Then we're going to see how that battery's energy is transformed. Remember, it doesn't die. That energy from that battery, what kind of energy would that be? Chemical. The chemical energy inside that battery is going to be transformed into electrical energy as it travels through this copper wire. This copper wire is known as a conductor. A conductor carries energy from one place to another. So this copper wire or conductor is carrying the chemical energy from this battery to this load. A light bulb, in this case, the load is a light bulb. A light bulb in this case is our load. That's the thing that's being powered by an electric circuit. And this is a great example of radiant light energy. So the three basic parts of an electric circuit is a power source, a conductor, and a load. So you may want to pause here because you do need to write this information down. The question we're going to write down here is, how is the law of conservation of energy illustrated within an electric circuit? Well, what does Miss Neville mean by that question? How is the law of conservation of energy? Energy cannot be created or destroyed, but only transformed. Illustrated. Whenever I see that word illustrated, I want to think of the word shown. So how can I see how energy is never gone, but transformed within an electric circuit? And the answer here is, it's always moving. Those blue dots that you're seeing in this picture right now, those represent something called electrons. Those are particles that are negatively charged, and they carry that energy, electricity, throughout that circuit in a circle. Okay? And so what we need to know here is, the answer to this question is the chemical energy inside of this battery is transformed. It doesn't start with this battery and it doesn't end at the battery. In fact, that chemical energy is transformed into electrical energy as it travels through the copper wire, and it's going to result in that radiant light energy in our light bulb. It's also important for us to know that the total amount of energy that came from this power source is transferred through that conductor and makes that light bulb light up. That's why, remember, we can, with the law of conservation of energy, we can only get what we give. That's why that bulb would be so much dimmer if I used a AAA battery, a smaller battery, and that bulb would be much brighter if I were to use a car battery, a much larger battery. In fact, it will probably make it explode. So we want to understand that the energy levels never change. The same amount of energy that's inside of that battery transfers into that light bulb. Okay? Energy is never lost. Energy is never lost. If we had to trace this energy transformation, we would see chemical energy is our starting energy, our producing energy. That energy is then going to transform into electrical energy as it travels through that copper wire. And then finally, it's going to transfer into radiant light energy. Remember, the energy doesn't stop there because that energy is moving in the flow of a circle, a cycle, yes, that energy is flowing within. Until that battery, until all the chemicals in that battery are used up and that battery, quotation marks, dies. So our next question that we need to write down, are batteries the only power source that can provide power to an electrical circuit? Absolutely not. We see here in our other gifts, a solar panel. You'll see these on top of some people's houses. A solar panel takes radiant energy from the sun, lets that energy travel down through a copper wire, and then it powers a load. In this case, the load is a battery. We also see here that with these rushing waters, remember we talked about the dam, when that water is behind that wall of the dam, it's potential energy. But as it rushes down that penstock, it's going to force that blades, the turbine, to spin, and it's going to produce or transform into electrical energy to power cities and towns. So we also see here a hand crank generator. Isn't this cool? Yes, the more energy that I put in using my muscles, I can power that load. So there's no battery. I'm the battery. I'm the power source. And so the more I turn it, the more energy is going to come to light those bulbs. So let's trace the energy transformations we see here. If we look back at our first example here, from the solar panel to the copper wire to this battery, what's our producing energy, our power source? Yep, radiant solar energy. The sun is giving energy here. It's then going to hit this solar panel and it's going to travel through this copper wire. What kind of energy would that be? Electrical energy. Electrical energy. And then finally, that electrical energy is going to charge a battery, possibly to power a house's lights and air conditioning at nighttime when the sun is gone. And what kind of energy is inside of a battery? Chemical energy. When we look at our second example here of our hydroelectric power system, when that water is behind the wall of the dam, that wall is closed, it's just stored energy, and the pressure is building, and the pressure is building, and the pressure is building. That is potential energy. It's then going to transform into, once the wall raises, the wall of that dam raises, it's going to transform into kinetic energy as that water rushes down the penstock. And then as that energy, that kinetic energy causes those fan blades on the turbine to spin, it's going to be transformed into electricity. Electricity. And so electrical energy. When we look at that hand crank generator, what is my energy type that tells me it's the energy of motion? Yeah, kinetic energy. Then that energy is flowing through that copper wire there. What kind of energy would that be? Electrical energy. And then it's going to power these three light bulbs. That's energy in the form of light. Radiant energy in the form of light. Please make sure you draw these pictures and you trace their energy transformation.